Uh, we are going to use two primitives, I mean, two simpler constructs uh, in the Grover's algorithm when we implement the Grover's algorithm as a quantum circuit. One of them is the phase inversion primitive, and the second one is the inversion around the mean primitive. Uh, this is what we mean by phase inversion. We'll use these two primitives. I mean, they will constitute the major two, components of the algorithm. Uh, Phase inversion is, let's suppose we have, zero to the n minus one. This is a quantum state uh, because there are n entries, 0 to n minus 1, capital N entries, but 2 to the n elements. We are representing these by n qubits. And each one of the states, or 2 to the n states of these n qubits, corresponds to one of the entries. So, and all of these entries, right? Because this is the quantum state we are talking about. You have cat x. Cat x is a particular entry now, and there are 2 to the n of them, and it has coefficients alpha sub x, right? Because it's a linear superposition of all these possible states. And if we plot these coefficients, let's say they are alpha sub x, and now x star is the solution, right? Phase inversion is you invert the alpha sub x that corresponds to x star from plus to minus, right? In other words, if you in the input, if you have this alpha sub x cat x, summed over all cat x, this input, if you apply a phase inversion to this, then you invert the phase alpha sub x star that corresponds the solution we are seeking for, cat x star. You change it from plus to minus. This is what we mean by phase inversion, right? And all the remaining other states, the coefficients for all the remaining states, they remain the same. They remain alpha sub x, cat x. So if x, cat x equals cat x star, in other words, if it is the solution that we are looking for, then invert the phase to minus alpha x star, as we keep alpha sub x the same. This is called inversion of the phase of the solution. And graphically we can represent this as assuming alpha x star is the solution, the coefficient alpha sub x star corresponding to the cat x star solution, we invert it. It becomes plus alpha x star becomes minus alpha x star. So this is in an operator form, we can represent this. We are going to prove, that this is actually this operator does this. What we said. It's actually not very difficult to see, but we'll show, formally, that this unitary operator does phase inversion. It inverts if we apply this unitary operator to the solution, cat x star, then it inverts the phase minus alpha sub x star of this particular input. So this corresponds to actually a phase oracle, right? The phase oracle we have been discussing. Because what phase oracle does is, if the input is cat x, now I'm omitting the other cat y, the ancillary bits, but since it is a phase oracle, right, the ancillary bit now is going to be cat minus state. I'm not showing it over here. This is a phase oracle that we discussed. So if the input is cat x, what phase oracle was doing is it brings in the function, right, to the exponent of the phase. So if f of x equals 1, in other words, if we have the solution that we are looking for, right, minus 1 to the 1 would be minus cat x. So once we have the solution, right, we have minus ket x star. In other words, it is inverting, the coefficient, the phase of the solution. But for all the other f of x, f of x would be 0, then you have a +1 phase in the front. So this phase oracle, in fact, represents this unitary transform, and it executes the phase inversion operation. The second primitive or construct we need is the inversion around the mean primitive. And this is what we mean by inversion around the mean. Again, let's suppose we plot alpha sub x, the coefficients of the 0 to capital N minus 1 of all the states, right? Quantum basis states, in this manner. And this has a mean mu, right? These coefficients, they have a mean mu, and this line represents the mean. Inversion around the mean means you take all these coefficients of the quantum states and you reflect them around this mu. In other words, this particular coefficient, for instance, becomes mu plus mu minus x, because this is mu minus x, right? This distance, this is mu, this line, the average value of all the coefficients, and this distance is mu minus x. So if you do mu plus mu minus x, right, you are reflecting, effectively this coefficient around the mean. So this is what we mean inversion around the mean. So by this transformation, the coefficients alpha sub x, they become, right, 2 mu minus alpha sub x. And another way to write this is mu plus mu minus x, right? Because you have mu, and then this distance you add, on top of mu to reflect, around the mean. So this is the transformation of the coefficients through this operation. Alpha sub x is transferred to 2 mu minus alpha sub x. So these two basic constructs actually will be sufficient, together with the standard, Hadamard operation, the standard Fourier sampling operation, will be sufficient to construct the Grover's algorithm, as we'll see shortly. And the way you would be able to represent this in a operator form, the inversion around the mean, is through this okay, so this was the phase inversion. Just one moment. Okay, yeah, I'll discuss it in more detail, when I go over the algorithm. But there is also an inversion, around the mean. The way we could represent this operation in an operator form. We'll discuss shortly when we get into the details of the algorithm. Okay, so let me skip this one now. So there is some discussion how this operator works. But before going into that, let me discuss this. Okay. Again, let me restate the problem. The problem is we are searching an unstructured database that is capital N equals 2 to the n elements, n qubits. So these quantum states of n qubits there are 2 to the n of them, 2 to the small n of them, and they represent the elements in an unstructured database. And the claim is that using a quantum algorithm, we can achieve a quadratic speedup with respect to the best known classical algorithm, because the best known classical algorithm is basically you go over all the elements in the database, and it is you need to have order capital N number of searches. This is the best classical algorithm. But quantum mechanically, Grover's algorithm achieves this unstructured database search problem, solves this problem in order square root of n number of operations. So that's a quadratic speedup. And formally, we can represent this problem as follows. Given a black box, an oracle, unitary U sub f, we'd like to find x equals x sub star. X sub star now is the solution such that f of x star equals 1. And as if this is not the solution, f of x equals 0. Right? So the problem is to find this x star that satisfies this equation, f of x equals 1. So X star is a database element that we are searching, and at the same time it solves this function. And we claim that this circuit achieves this. So let's consider this quantum circuit. In the input, we have n bits of cat zeros, and we have Hadamard tensored n applied on these n qubits. This is the quantum Fourier sampling construct, right? We discussed the primitive. And then U sub f is the phase inversion primitive we discussed. This H tensor n, U sub f0, H tensor n, this is called the diffusion operator. The diffusion operator we denote by V, and V equals this construct. It is H tensor n, U sub f0, and H tensor n. And this part is phase inversion, and this part is inversion around the mean. So these two unitary operations we derived. Phase inversion unitary operator that we just discussed. And the diffusion operator, in other words, inversion, around the mean operator. This construct does this, and we repeat this phase inversion times V. I mean, this times this R times. We'll discuss what R is. What is the optimum value of R. We repeat this circuit R times, and the claim is at the end of this iteration, the output, when we make a measurement, the output is the element the database entry that we are searching for. So the database entry is again, it's an n-bit string, right? It's one of the entries in the database. And we claim that when we make a measurement after R repetitions, right, we obtain in the output the entry that we are looking for. We are, in other words, we are proving that the output Y equals X star, where X star is the X, that satisfies f of X prime equals 1 with high probability. So we'll prove this. And we typically we do these things, we just follow the circuit. So at each stage of the circuit, we compute the quantum state. Typically, this is how we address these kind of proof problems. We just go over the stages of the circuit one by one, and in the end we show that the output corresponds to what we are looking for. Uh, Again, we said U sub f, right? This is the phase inversion. By definition of the phase oracle, right? U sub f applied to cat x equals -1 to the f of x cat x. Right? This was how a phase oracle behaved. In other words, if we apply this phase inversion U sub f operator to the solution state, to x star, right? Now f of x for x star equals 1, so you would have -1 to the first power ket of x star, which is minus uh, ket of x star. So this was what phase inversion was doing. It is inverting, the phase in the front of the state that we are interested in. And also, we can see that for all the other states where f of x equals 0, right, you have -1 to the 0th power, which is +1. And so u of f of u sub f of cat x would equal to x. So there is no phase inversion. We only invert the phase that for the state that we are searching for. And we said this u sub f of cat x, right, which we denoted as this operator, does this. And it's, as I said, it's very easy to see. So let's suppose you apply this to the solution state, right? In other words, if cat x equals cat x star, right, this inner product would be 1, because, cat bra x star inner product with cat x star would be 1, right? So, and you have I, the identity matrix multiplied with the cat x state, right? Cat x star state would be cat x star. So you would end up with and cat x star due to this I -2, this -2 coefficient, cat x star equals minus cat x star, right? It is, so we have seen, that if you apply this operator to the x star state that we are looking for, you get a phase inversion here. You have minus cat x star. So, but all the other x, right? For all the other cat x states other than the x star state, this inner product would be 0, right? So you would end up with, so this part of the equation will be 0, but I times cat x would be cat x. So you would obtain this, u sub f cat x operating on cat x equals cat x for all the cat x that is different, from cat x star. Okay. So this is the phase inversion part. This is what u sub f does. Let's see inversion around the mean. What the second part does. This part, because we are claiming we apply phase inversion and then we apply inversion around the mean r times altogether. This circuit repeat r times, and in the end, in the output, we have the solution. Cat x star with high probability. Okay, we claim this is the operator for the inversion around the mean. And if you apply, and this is cat 0 to tensor n times, bra 0 tensor n times minus the identity operator. We claim this is the inversion operator. Again, it's easy, not difficult to show. That this does the inversion operation that we discussed before. Let me actually just summarize, what we have done up till now, because we have discussed many things and there are many steps. I think we need to just summarize, what we have done so far. This is the circuit we are discussing, right? This is the phase inversion part of the circuit, and this is the inversion around the mean part of the circuit. And we are claiming this circuit, if we apply R times, right, repetitively to this cat zero tensor n input state, in the output, when we do the measurement, we obtain the cat x star state that we are looking for. So this part was phase inversion, and this part was V equals H tensor n, U sub F0, H tensor n, this part of the circuit, inversion around the mean, primitive. And we said U sub F, phase inversion was in operator form, I minus 2 cat x star, bra x star, right? This is an output product, so this is an operator, and I is an operator. So this is U sub F is the operator, and we have shown that this does phase inversion on the state cat x star, and this is inversion around the mean U sub F0, right? This 2 cat 0 bra 0 tensor n times minus I. This is the inversion around the mean. And the V operator is this entire thing, right? H tensor n, U sub F0, which is this operator, H tensor n, right? This is the V operator. So what we are saying is, if you apply U sub F V, right? This is U sub F V, R times, right? Repeated R times to this input, you obtain the solution cat x star in the output. This is what we have done so far. I would like to go through a geometric analysis first, but if you like, let's give so we'll continue with the proof of the Shor's algorithm by going through the circuit step by step, stage by stage. Let's again considering the circuit. In the input, right, we have cat 0 state tensored n times, in other words, n cat 0 states. And then we applied Hadamard tensored n state to this. So this is my input, cat 0 tensored n times, and I apply this Hadamard tensored n times to this state at step 1. Now we are here. We are here at this step, first step, this circuit. And through our discussions, of the Fourier sampling, right, primitive, we know that this equals 1 over 2 to the n over 2. This was just a normalization constant because we have 2 to the n of these cat x states, and each one of them has a coefficient of 1 over 2 to the n over 2, because if you square and add up all the coefficients, right, it should add up to 1. All quantum states, right, are normalized, and the square sum of all the coefficients should add up to 1, and this is the normalization constant for that. And this is an equal linear superposition of all the cat x states, x being, again, x element of all the n-bit strings of 0 to 1. It's a linear superposition of all the possible n such bits. This was what this Hadamard operation applied on a cat 0 tensor n state was doing. So this is the output of the first stage. We are right here. And let's denote this but by cat S. Cat S is this equal sum of all the cat X states. We note that this, let's work out this, what exactly this does, V inversion around the mean operator does. So this inversion around the mean operator was H tensor n, U sub F0, H tensor n. Right? This, now we are talking about this part of the circuit, H tensor n times U sub F0 times H tensor n. And we said this is the operator for U sub F0, inversion around the mean operator. The first part would be H tensor n, 2 times, 2 is a number, so we can take it out of the operator. This is H tensor n, cat 0, bra 0, right, this bra 0, H tensor n, minus H tensor n times I, this I, H tensor n. But we know that H tensor n and H tensor n is self-inverse. H tensor n is self-inverse of H tensor n. In other words, the inverse of H tensor n is also H tensor n. It's just like H is inverse of itself. The Hadamard operator is the inverse of itself. So likewise, the Hadamard tensor n times is also inverse of itself. So this part is just I. The first part, 2 times Hadamard applied on 0, we just saw, that it is cat S. It is this equal linear superposition of all the cat X states. So this part becomes 2 cat S. And this is just the dagger of this. It's just a bra cat S. This is bra cat 0 Hadamard tensor n. It's just the dagger, of this first part. In other words, you convert the cat state to a bra state and take the complex conjugate of the all the components. So this is this first part. It's 2 times cat S, bra S, and this was just the identity operator minus I. So this is just what we mean, by this V operator. So we converted, this V operator to this form. Step 2, we apply V U sub F R times, right? We apply V U sub F R times, because we said we repeat, this circuit R times. Okay. And let's see what this does. There are 2 ways actually to prove this. One is this geometric argument, and another argument I'll also discuss, afterwards if we have time, or maybe next time. The geometric argument is as follows. Now consider the space spanned by cat X star and cat X star perpendicular. Right? Cat X star is one of that's the state actually that we are looking for. And cat X star perpendicular are all the other states, right? Because these states, quantum states, they form an orthonormal basis. So all the other remaining states, they are actually perpendicular to the cat X star. So this cat X star perpendicular, it contains all the states other than cat X star. And this space we can represent this as follows. cat x star perpendicular is actually the sum of all the states, and this is the normalization constant. Now we don't, it's all the state other than cat x star. This is supposed to be other than. It's not cat x equals x star. Cat x not equal to x star. So it's the sum of all the other states other than x star, and this is the normalization constant. This normalization constant is because of now we have one less. We don't have 2 to the n states in this set. Now we have 2 to the n minus 1 states. So this, in a two-dimensional space, this vector and this vector, they form a basis, right? Because they are perpendicular. And if you take the inner product, they are perpendicular, as you see. And so they form a basis. They are orthonormal. They form an orthonormal basis. And the cat S state now can be represented as a linear combination of these bases, right? Cat S, it's the state that we defined as this. You know, it's the linear superposition of all the cat X states. Hadamard applied on the cat 0 state. This was the definition of the cat S state. So cat x s is just a state. So we said these two states, they form a basis. So we can represent cat s as a linear superposition of these two states. So you can check that as it should be. Cat s now it's in this representation, it's normalized. In its length bra s inner product cat s is normalized to 1. You can easily show this. So let's define this cosine theta over 2 and sine theta over 2 as these coefficients. In other words, we define theta, the angle theta, such that cosine theta over 2 equals this coefficient, square root of 2 to the n minus 1 over 2 to the n, this cosine theta, and sine theta over 2 is this coefficient, 1 over square root of 2 to the n. And this is the cat S state. I mean, this is nothing but, you know, we are redefining these coefficients in terms of cosine theta over 2 and sine theta over 2, because we are going to develop a geometric argument. And you can also now check that the length of this cat S is also 1, because cosine square 2 over 2 plus sine square 2 over 2 equals 1. If you solve this, right, for theta, now theta equals 2 times, using this expression, theta equals 2 times arc sine 1 over 2 to the n, if you solve for theta in this equation. Now let's follow the steps of the algorithm, you know, given these definitions again, once more. Now again, following the circuit, we have we apply the Hadamard on cat 0 state, right? And we obtain the cat S state, which was this. Now we operate with the U sub f operator, right? Inversion around the mean, which was I minus 2 cat x star bra x star. This was the reflection. It is inversion around the mean, but also at the same time reflecting cat S around cat x star perpendicular. So we'll see, you know, graphically. But we have shown that this circuit corresponds to phase inversion, right? Alpha sub x star equals minus alpha sub x star. So, and then we operate with these are the stages. Now I'm following the circuit. First, we do this Hadamard, and then we do phase inversion, and then we do this inversion around the mean. We apply these two operators. Okay. And the step 2 was apply this R times. You know, repeatedly V times the U sub F operator on the cat S state. Okay. Okay. So let's see what this means graphically. You know, these operations, what they mean graphically. Uh, we said this ket x star and ket x star perpendicular, they form a basis, right, in a two-dimensional space, these two vectors. And this is the ket s state, right? So this is the step one of the circuit, ket s. What we do is we apply u sub f, right? U sub f was this operation. So this operation reflects around cat x star. This is because when you reflect cat x around cat x star, effectively what we are doing is you are doing phase inversion, you know, of this cat of the cat s star, right? So you start with cat s, you apply u sub f, you reflect around the cat x star perpendicular. So at step two, after you apply u sub f phase inversion, the vector is here, right? And then at step three, you apply the v operator, v to this u sub f cat s. You apply v operator, and v operator is defined as this. And this is a reflection around ket S, right? This is the ket S state. Ket S state had an angle theta over 2, right? So we first applied U sub f. We have obtained this state. U sub f was a reflection around ket x perpendicular. And then we apply f. Now f reflects this u sub f s around the ket s state. In other words, this angle was theta over 2 plus theta over 2 theta. It adds, you know, another theta degrees to ket s. So each cycle, right? Each cycle of this v u sub f brings this state closer to ket x star, right? At each cycle, we have theta degrees of rotation of this ket s state, right? And when you apply this v u sub f r times, you are effectively rotating, you know, this ket s state by the angle r theta. So you apply this circuit r times, you know, sufficiently many times so that eventually this starting state ket s approaches ket x star, which is the solution, right? Our objective is to reach solution. So this is a sort of a geometric argument, you know, that shows this circuit we discussed. It starts with ket s, right, state, and first you apply phase inversion u sub f on ket s. So that's a reflection around this ket x star perpendicular. And then you apply v times u sub f ket x s. Now this is a reflection of the new vector around ket s. In other words, you add another theta, you know, degrees of angle. So each time you apply the circuit, you are basically moving, you know, this ket s state closer and closer to the ket x star state, which is the desired solution. So what is R? You know, what is an optimal R? Because each time you rotate this ket s vector by an angle theta, but if you over apply, in other words, the number of iterations, if it is over the number of required number of iterations, then you basically rotate this vector around. So you miss, you miss the optimal state cat x star that you are going after. So what is the optimum number of rotations are? It's also not difficult to show. For our optimal, we need r theta plus theta over 2, because we start, remember, we start this angle theta over 2. And at each iteration, we rotate this cat s vector with an additional theta. So this theta over 2 plus r theta introduced by r times application, of the circuit. So this is supposed to equal approximately equal pi over 2, because when this angle equals pi over 2, right? This angle is pi over 2. We reach the optimal solution. This is okay. So from here, it's easy to solve for the optimal r. Because now our solving this solution, right? R theta equals r theta plus theta over 2 equals pi over 2. Solving for r, we have pi over 2 theta minus 1 over 2. And now theta was, as we derived before, was this arc sine, 2 theta was 2 arc sine 1 over square root of 2 to the n, right? This is theta. And for large x, the arc sine x approaches x. So using this, r approximately equals pi over 4, 2 to the n over 2. So that means by repeating the circuit in the order 2 to the n over 2, remember 2 to the small n equals capital N, the number of entries in the database, and this equals order square root of large N, number of R iterations, we are able to reach the optimal solution. So this is a quadratic speed up, with respect to the best known classical algorithm. Okay, so in a nutshell, this is, I think I'll conclude now, but I'll go over this because this is a rather complicated algorithm. This is one of the most complicated algorithms that we'll see. This algorithm plus the Shor's algorithm is a little longer than this. I'll go over these arguments at the beginning of our next session. I'll summarize, all the results, in a neater fashion, and I'll also go over a numerical, an operational argument, to solve, to prove this theorem, because this was a geometric kind of proof. I mean, you start with the cat S vector, and by applying phase inversion and inversion around the mean, these operators, this cat S state approaches cat X star, which is the solution we are looking for. This is the geometric argument that we discussed. But next time I'll summarize all these arguments, plus I'll also introduce another approach for the proof, of Grover's algorithm. I suggest you go over this